Section 43 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain, recorded by Peter Yearsley. Chapter 18. Silicon, Carbon, Boron. Silicon and Silicates. In assaying, more especially products direct from the mine, there is always found, when the rock is siliceous, a quantity of white sandy-looking substance insoluble in acids, which is sometimes accompanied by a light gelatinous material, very difficult to filter. This is variously described as insoluble sand, insoluble silicates, gangue, or rocky matter. It may be pure quartz, but oftener it is mixed with silicates from the rock containing the mineral. Some silicates, but not many, are completely decomposed by boiling with hydrochloric acid or aqua regia, and others are partly so. They yield a gelatinous precipitate of silica, which greatly interferes with the filtering. It is a common practice with assayers to carry the first attack of the sample with acids to dryness, and to take up with a fresh portion of acid. By this means the separated silica becomes granular and insoluble, and capable of being filtered off and washed with comparative ease. This residue may be ignited and weighed, and be reported as so much % of silica and silicates insoluble in acids. Unless specially wanted, a determination of its constituents need not be made. When required, the analysis is best made on the ignited residue, and separately reported as analysis of the insoluble portion. Silicon only occurs in nature in the oxidized state, but the oxide generally known as silica, SiO2, is common, being represented by the abundant minerals, quartz, flint, etc. Silica, combined with alumina, lime, oxide of iron, magnesia, and the alkalis, forms a large number of rock-forming minerals. Most rock masses, other than limestones, contain over 50% of silica. The following are analyses of some of the commoner silicates, but it must be noted that these minerals often show great variation in composition. This is more especially true of chlorite, schorl, hornblende, and augite. Reader's note: in the following table, the constituents of the minerals are given by name only. Their formulae are as follows: silica SiO2, alumina Al2O3, ferric oxide Fe2O3, ferrous oxide FeO, lime CaO, magnesia MgO, potash K2O, soda Na2O. End reader's note. Potash feldspar, 65.2% silica, 18.2% alumina, 0.2% ferric oxide, ferrous oxide not found, lime not found, magnesia not found, 14.7% potash, 1.5% soda. Soda feldspar, 67.0% silica, 19.2% alumina, ferric oxide not found, 0.3% ferrous oxide, 1.2% lime, 1.8% magnesia, 2.2% potash, 7.2% soda. Lime feldspar, 43.3% silica, 35.4% alumina, ferric oxide not found, 1.3% ferrous oxide, 17.4% lime, 0.35% magnesia, 0.5% potash, 0.9% soda. Potash mica, 45.7% silica, 33.7% alumina, 3.1% ferric oxide, ferrous oxide not found, lime not found, 1.1% magnesia, 7.5% potash, 2.8% soda, 0.8% fluorine, 4.9% water. Magnesia mica, 39.1% silica, 15.4% alumina, 7.1% ferric oxide, ferrous oxide not found, lime not found, 23.6% magnesia, 7.5% potash, 2.6% soda, 0.7% fluorine. Hornblende, 40.6% silica, 14.3% alumina, 5.8% ferric oxide, 7.2% ferrous oxide, 12.5% lime, 14.0% magnesia, 1.5% potash, 1.6% soda. Augite, 50.0% silica, 3.7% alumina, 2.4% ferric oxide, 6.6% ferrous oxide, 22.8% lime, 13.5% magnesia, potash not found, soda not found, 0.1% manganese oxide, MnO. Almandine, garnet, 39.7% silica, 19.7% alumina, ferric oxide not found, 39.7% ferrous oxide, lime not found, magnesia not found, potash not found, soda not found, 1.8% manganese oxide, MnO. Chlorite, peach, 32.1% silica, 18.5% alumina, ferric oxide not found, ferrous oxide not found, lime not found, 36.7% magnesia, potash not found, soda not found, 12.1% water. Schorl, 37.0% silica, 33.1% alumina, 9.3% ferric oxide, 6.2% ferrous oxide, 0.5% lime, 2.6% magnesia, 0.7% potash, 1.4% soda, 7.7% barium oxide, B2O3, 1.5% fluorine. China clay, 46.7% silica, 39.6% alumina, ferric oxide not found, ferrous oxide not found, lime not found, magnesia not found, potash not found, soda not found, 13.4% water. Talc, 61.7% silica, alumina not found, ferric oxide not found, 1.7% ferrous oxide, lime not found, 31.7% magnesia, potash not found, soda not found, 3.8% water. Serpentine, 42.9% silica, alumina not found, ferric oxide not found, 3.8% ferrous oxide, lime not found, 40.5% magnesia, potash not found, soda not found, 12.6% water. Olivine, 39.3% silica, alumina not found, ferric oxide not found, 14.8% ferrous oxide, lime not found, 45.8% magnesia, potash not found, soda not found. Silicon, from a chemical point of view, is an interesting body. It combines with iron to form a silicide, and is present in this condition in cast iron. Only in the case of the analysis of this and similar substances is the assayer called on to report the percentage of silicon. Silicon is readily converted into silica by the action of oxidizing agents. Silica forms only one series of salts, the silicates, which have in many cases a complex constitution. Thus there are a large number of double silicates, which vary among themselves not only in the relation of base to acid, which is the essential difference, but also in the ratio of the bases between themselves, which varies with almost every specimen. Silica is detected by heating the substance with a fluoride and sulfuric acid in a platinum crucible. On holding a rod moistened with a drop of water over the escaping fumes, the white crust of silica formed on the drop of water shows its presence. The insolubility of a fragment of the mineral in a bead of microcosmic salt is also a very good test. The fragment on prolonged heating does not lose its angular form. There is no dry assay for this substance, nor volumetric method. When the determination is required, it is carried out gravimetrically, and generally by the following plan. If the sample contains oxides, sulfides, etc. in any quantity, these are first dissolved out by treatment with acid, evaporated to dryness, taken up with hydrochloric acid and filtered. The dried residue is treated in the same way as the silicates. Some silicates are completely decomposed by such treatment, but it saves time, unless one is sure that no undecomposable silicate is present, to treat these in the same way as the others. On the other hand, there are some silicates which are only attacked with difficulty even by fusion with alkaline carbonates. Consequently, it is always well to have the substance reduced to the finest state of division by careful powdering, as this greatly assists the subsequent action. With very hard silicates, the grinding away of the mortar in this operation will be perceptible. The foreign matter thus introduced must not be ignored. Previously igniting the substance sometimes assists the powdering, but it is best to use a steel mortar. The particles of steel can be removed by a magnet, or where the nature of the substance will allow it, by boiling with a little dilute hydrochloric acid. The dried and powdered material is intimately mixed with 4 times its weight of fusion mixture in a platinum crucible or dish. It is then moderately heated over a Bunsen burner and afterwards more strongly fused over a blast or enclosed in a clay crucible in the wind furnace. The action is continued until the fused mass is perfectly tranquil. With very refractory substances, the action must be long continued at a high temperature. When sufficiently cold, the crucible is examined to see that no particles of foreign matter are adhering to its outer surface. It is then transferred to a 5 or 6 inch evaporating dish, where its contents are acted upon with warm water for some time. The melt will slowly dissolve, but the solution should be hastened by keeping the liquid moderately acid with hydrochloric acid. When the melt has dissolved, clean and remove the platinum dish and evaporate the solution to a paste. Continue the evaporation to dryness on a water bath, not on the hot plate, and whilst drying stir with a glass rod, feeling at the bottom of the dish for any unfused particles, which, if present, can be detected by their grittiness. If there is much grit, it will be necessary to repeat the assay, but with a small quantity it will only be necessary to refuse the grit and silica after ignition. During solution of the melt and evaporation, which may be carried on together, a clear solution will not be obtained. A flocculent silica will separate out, and towards the end of the evaporation the mass will get gelatinous. The drying of the jelly must be finished on the water bath. First, because at this temperature the silica is rendered insoluble in hydrochloric acid, whilst the solubility of the alumina, iron, etc. is unaffected, which would not be the case at a much higher temperature. And second, because the gelatinous residue requires very cautious drying to prevent loss from spurting. When dry, the substance is moistened and heated with strong hydrochloric acid, and the sides of the dish are washed down with water. The silica is washed by decantation 2 or 3 times with hydrochloric acid and hot water before being thrown onto the filter. The filtrate is again evaporated to dryness, taken up with a little hydrochloric acid and water, and again filtered. The residue on the filter is silica. The 2 lots of silica are washed free from chlorides with hot water, dried on an air bath, transferred to a platinum crucible, ignited gently at first, at last strongly, over the blast or in a muffle, cooled in a desiccator, and weighed. The white powdery precipitate is silica, SiO2, and its weight multiplied by 100 and divided by the weight of ore taken gives the percentage of silica in the sample. Where the percentage of silicon is wanted, which is very rarely the case, it is got by multiplying this result by 0.4667. It is always necessary to examine the purity of the body weighed as silica. This is done by refusing the material weighed and redetermining the silica in it, or, better, by mixing a weighed portion in a platinum dish with a little strong sulphuric acid, covering with hydrofluoric acid, and evaporating. In the latter case, the silica will be converted into fluoride, which will be driven off, and the impurities will be left behind as sulfates of barium, phosphate and oxide of tin, titanium, etc. This must be weighed and deducted from the weight of the silica. In a complete examination of a silicate, it should be treated with the precipitate containing alumina, ferric oxide, etc. Examination of silicates. The student interested in the analysis of rocks and rock-forming minerals is advised to consult a valuable paper by Dr. W. F. Hillebrand in the Bulletin of the United States Geological Survey, No. 148, to which I am very largely indebted in the revision of the following pages. Moisture. 5 grams of the powdered sample is dried between watch glasses in the water oven for 2 hours, or till its weight is constant, and the loss is reported as water lost at 100 degrees centigrade. The rest of the determinations are made on this dried mineral. combined water, etc. Weigh up 1 gram of the substance and ignite over the blowpipe for some time in a platinum crucible. Cool in a desiccator and weigh. Record the loss as loss on ignition, not as combined water. Silica. The ignition should have been performed in an oxidizing atmosphere in a muffle or over a slanting blowpipe flame. This will ensure the oxidation of any pyrites or other sulfide present, which, if unoxidized, would injure the crucible in the next operation. The ignited residue is mixed with 6 or 7 grams of anhydrous sodium carbonate. This reagent should be the purest obtainable, but its purity should be checked, or rather its impurities should be determined by running a check or blank assay with 10 grams of it through the stages of the analysis. The impurities will be chiefly silica, alumina and lime, and altogether they ought not to exceed 1 milligram. The crucible with the mixture is heated at first gently over a Bunsen and afterwards more strongly in an oxidizing atmosphere in a muffle or over the blowpipe. The fused mass is allowed to cool in the crucible and is then dissolved out in a basin with water and a small excess of hydrochloric acid. After the removal and cleaning of the crucible, the liquor is evaporated almost to dryness. Dr. Hillebrand advises stopping short of complete dryness. The residue is taken up with a little hydrochloric acid and water and filtered and washed. The liquor, including the washings, is again evaporated and taken up with water and a little acid. Usually about 1% of silica will be thus recovered. It is to be filtered off and washed and added to the main silica. The filtrate is reserved. The silica, thoroughly washed, is dried and ignited at a high temperature for 20 or 30 minutes. It is then weighed in a platinum crucible. After weighing, it is treated with hydrofluoric acid and a little sulfuric, carefully evaporated and ignited strongly. The residue, which in extreme cases may amount to 2 or 3% of the rock, is weighed and deducted from the weight of the impure silica. It is retained in the crucible. Alumina, etc. The filtrate from silica is treated by the basic acetate method. That is, it is first treated by a cautious addition of a solution of soda, almost to the point of producing a precipitate, in order to neutralize the excess of acid. 2 or 3 grams of sodium acetate are added, and the whole boiled for a minute or so. The precipitate is filtered off and washed only slightly. Save the filtrate. The precipitate is dissolved in hydrochloric, or perhaps better in nitric acid, and is reprecipitated by adding an excess of ammonia and boiling. The precipitate is filtered and washed with water containing 2% of ammonium nitrate. Both filtrates are evaporated separately to a small bulk, a drop or two of ammonia being added to the second towards the finish. They are next filtered into a 6 or 8 ounce flask through a small filter, the second filtrate coming after, and serving in a manner as wash water for the first. Footnote: if the dishes show a manganese stain, wash them out with a few drops of hydrochloric and sulphurous acids. Pass the acid liquor through the same small filter, but collect the liquor apart. Make ammoniacal and again pass through the filter, this time collecting the liquid with the main filtrate. End footnote. The 2 washed alumina precipitates are dried and placed in the platinum crucible containing the residue from silica after treatment with hydrofluoric acid. They are then ignited in an oxidizing atmosphere at a high temperature for about 10 minutes. The weight, including that of the residue from the silica, is noted as that of alumina, etc. The weighed oxides are next fused with bisulfate of potash for some hours. The bisulfate should have been first fused apart until the effervescence from the escape of steam has stopped. The melt is dissolved out with cold water and dilute sulfuric acid, and any insoluble residue is filtered off, washed, ignited, and weighed. The filtrate is reserved for determinations of iron and titanium. The residue, after weighing, may be treated with hydrofluoric acid and sulfuric acids for any silica which would be determined by loss. Footnote: this rarely amounts to more than 1 milligram. End footnote. It may be tested for barium sulfate by treatment with hot strong sulfuric acid, in which this salt dissolves, but is again insoluble, and so comes out as a white precipitate, on diluting with cold water. The acid also must be cold before adding the water. The filtrate containing the iron is reduced with sulphuretted hydrogen, boiled till free from that gas, filtered, and titrated with a standard solution of permanganate of potassium. The iron found is calculated to ferric oxide by dividing by 0.7. The iron solution after titration serves for the determination of titanium oxide, TiO2. This is done colorimetrically by adding peroxide of hydrogen, free from hydrofluoric acid, and comparing the brown colour produced with that produced by the addition of a standard solution of titanium to an equal volume of water containing sulfuric acid. Footnote: to make this, dissolve 1 gram of titanium oxide, fusing for some time with an excess of bisulfate of potash, and dissolve out with cold water and sulfuric acid. Dilute to 1 litre, having previously added not less than 50 cc of strong sulfuric acid. 1 cc will contain 0.01 gram of TiO2. For the assay, take 10 cc of this, add 2 cc of peroxide of hydrogen, and dilute to 100 cc. Run this from a burette into the flask until the colour equals that of the assay. Each cc equals 1 mg of TiO2. Fluorides must be absent. End footnote. The alumina is determined by difference. From the weight of the combined precipitate which has been recorded as alumina, etc., deduct 1. The residue insoluble after fusion with bisulfate, 2. The ferric oxide, 3. The titanium oxide, and 4. The phosphoric oxide, P2O5, the amount of which is subsequently determined in a separate portion. This gives the alumina. Manganous oxide, etc. The filtrate from the alumina, etc., contained in a 6 or 8 ounce flask, which it nearly fills, is made slightly alkaline with ammonia and treated with a small excess of ammonium sulfide. The flask is then corked and placed on one side for some time, a day or so that the manganese sulfide may separate. The precipitate is filtered off and washed with water containing ammonium chloride and a few drops of ammonium sulfide. The filtrate is reserved for lime, etc. The precipitate is digested with sulphuretted hydrogen water, to which 1/5 of its volume of strong hydrochloric acid has been added. This dissolves the sulfides of zinc and manganese. Any black residue should be tested for copper and perhaps nickel. The solution is evaporated to dryness, taken up with a little water, and treated with a small excess of solution of carbonate of soda. It is boiled and again evaporated, washed out with hot water, and filtered onto a small filter, dried, ignited, and weighed as Mn3O4. It is calculated to MnO. It may contain, and should be tested for, oxide of zinc, which, if present, must be deducted. If the dish becomes stained during evaporation, take up with a few drops of hydrochloric and sulphurous acids, evaporate, and then treat with carbonate of soda. Lime, etc. The filtrate from the manganese sulfide is boiled, and without cooling treated with ammonium oxalate in solution, which also should be heated to boiling. The liquid is filtered off and reserved for magnesia. The precipitate is dissolved in very little hydrochloric acid and reprecipitated by adding ammonium oxalate and ammonia to the boiling solution. The filtrate and washings from this are reserved for magnesia. The precipitate is either dissolved in dilute sulphuric and titrated with permanganate of potash, as described under lime, or it is ignited and weighed as oxide. In this last case it may be examined for barium and strontium, the former of which will rarely be present. Magnesia. The filtrate from the first lime precipitate is treated with sodium phosphate and ammonia and allowed to stand overnight. It is then filtered. The precipitate is dissolved in hydrochloric acid. The solution is filtered into the beaker containing the solution from the second lime precipitate. Ammonia and sodium phosphate are again added, and the precipitate after standing is filtered off, washed with water containing ammonia. It is then dried, ignited, and weighed as magnesium pyrophosphate. This is calculated into magnesia. Potash and soda. Weigh out 0.5 gram of the dried ore and mix with an equal quantity of ammonic chloride, and to the mixture add gradually 4 grams of calcium carbonate (precipitated). Introduce into a platinum crucible and cover loosely. Heat, at first gently, and then at a red heat for from 40 to 60 minutes. Transfer to a porcelain dish and digest with 60 or 80 c.c. of water. Warm and filter. To the filtrate add ammonic carbonate and ammonia, and filter. Evaporate the filtrates to dryness, adding a few drops more of ammonic carbonate towards the end. When dry, heat gently, and then raise the temperature to a little below redness. Dissolve in a small quantity of water, add a drop of ammonic carbonate, and filter through a small filter into a weighed platinum dish. Evaporate, ignite gently, and weigh. The residue contains the soda and potash of the mineral as chlorides. To determine the proportion of potassium, dissolve this residue in a little water, add platinum chloride in excess, evaporate to a paste, extract with alcohol, decant through a small weighed filter, wash with alcohol, and dry at 100 degrees centigrade. Weigh. The substance is potassium platinic chloride. Note 2 kCl.PtCl4. Its weight multiplied by 0.1941 will give the weight of potash, K2O. To find the proportion of soda, multiply the weight of the potassium platinic chloride by 0.306. This gives the weight of potassium chloride. Deduct this from the weight of the mixed chlorides first got. The difference will be the sodium chloride, which weight multiplied by 0.53 will give the weight of soda, Na2O. Ferrous oxide. When a qualitative test shows both ferric and ferrous oxide to be present, the proportion of the ferrous oxide must be separately determined. The finely ground mineral mixed with dilute sulfuric acid is treated on a water bath with hydrofluoric acid. Solution is best effected in an atmosphere of carbonic acid. In about an hour the decomposition is complete, and the solution is diluted with cold water and titrated with the solution of bichromate or of permanganate of potassium. The iron found is multiplied by 1.286 and reported as ferrous oxide. To find the proportion of ferric oxide, the ferrous iron found is multiplied by 1.428, and this is deducted from the weight of ferric oxide obtained by precipitation with ammonia. The ammonia precipitate contains the whole of the iron as ferric oxide, hence the necessity for calculating the ferrous oxide as ferric and deducting it. Phosphoric oxide, P2O5. Weigh up 5 grams of the finely divided and dry sample and digest with 10 or 20 c.c. of nitric acid. Evaporate to dryness on the water bath, take up with a little dilute nitric acid, dilute with water, and filter. Add a few grams of ammonic nitrate and 10 c.c. of ammonium molybdate solution. Heat nearly to boiling and allow to settle. Filter off and wash the yellow precipitate. Dissolve with dilute ammonia, add magnesia mixture, and allow to stand overnight. Filter, wash with dilute ammonia, dry, ignite, and weigh as pyrophosphate of magnesia. The weight multiplied by 0.6396 gives the weight of phosphoric oxide. Soluble silica. Some silicates are acted on by hydrochloric acid and leave on evaporation a residue which, when the soluble salts have been washed out, consists generally of the separated silica with perhaps quartz and unattacked silicates. It should be ignited, weighed, and boiled with a solution containing less than 10% of caustic soda. This dissolves the separated silica. The liquor is diluted, rendered faintly acid, and filtered. The residue is washed, ignited, and weighed. The loss gives the soluble silica. Estimation of silica in slags. Note: ferrous silicates. End note. Take 1 gram of the powdered slag, treat with aqua regia, evaporate to dryness, extract with hydrochloric acid, filter, dry, ignite, and fuse the ignited residue with fusion mixture. Then separate and weigh the silica in the usual way. Slags are for the most part decomposed by boiling with aqua regia, but it will be found more convenient and accurate to first extract with acids and then to treat the residue as an insoluble silicate. Estimation of silica and insoluble silicates in an ore. Take 2 grams of the powdered mineral, evaporate with nitric acid, if sulfides are present, treat the dried residue, or the original substance if sulfides are absent, with 10 or 20 cc of hydrochloric acid. Again evaporate to dryness, take up with dilute hydrochloric acid, filter, wash, ignite and weigh. Estimation of silicon in iron. Place 2 grams of the metal, borings or filings, in a 4-inch evaporating dish and dissolve, with aid of heat, in 25 cc of dilute nitric acid. Evaporate to complete dryness, take up with 20 cc of hydrochloric acid and allow to digest for 1 hour. Boil down to a small bulk, dilute with a 5% solution of hydrochloric acid, boil and filter. Wash with acid and water, dry, ignite in a platinum crucible and weigh the SiO2. This, multiplied by 0.4673, gives the weight of the silicon. The percentage is calculated in the usual way. Practical exercises. 1. A certain rock is a mixture of 70% of quartz, 25% of potash feldspar and 5% of potash mica. What percent of silica will it contain? 2. 2 grams of a mixture of silica and cassiterite left after reduction in hydrogen 1.78 grams. Assuming all the oxide of tin to have been reduced, what will be the percentage of silica? 3. The formula of a compound is 2FeO.SiO2. What percentage of silica will it contain? 4. 2 grams of a sample of cast iron gave 0.025 gram of silica. Find the percentage of silicon in the metal. 5. What weights of quartz and marble, CaCO3, would you take to make 30 grams of a slag having the formula CaO.SiO2? End of section 43. Section 44 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 18. Silicon, Carbon, Boron. Part 2. Carbon and Carbonates. Carbon compounds enter so largely into the structure of organized bodies that their chemistry is generally considered apart from that of the other elements, under the head of organic chemistry. Carbon occurs, however, among minerals not only in the oxidized state as carbonates, but also in the elementary form, as in diamond and graphite, and combined with hydrogen, oxygen, etc., as in petroleums, bitumens, lignites, shales, and coals. In small quantities, organic matter is widely diffused in minerals and rocks. In shales and clays it may amount to as much as 10 or 20%, mainly as bituminous and coaly matters. The assayer has only to take account of the organic matter when it is of commercial importance, so that in assays it is generally included under loss on ignition. In coals, shales, lignites, etc., the carbon compounds are, on heating, split up into oils and similar compounds. The products of distillation may be classified as water, gas, tars, coke, and ash. The assay of these bodies generally resolves itself into a distillation, and, in the case of the shales, an examination of the distillates for the useful oils, paraffin, creosote, etc., contained in them. Elementary carbon is found in nature in 3 different forms, but these all react chemically in the same way. They combine with oxygen to form the dioxide. Footnote: C plus O2 yields CO2. End footnote. The weight of oxygen required to burn a given weight of any form of carbon is the same, and the resulting product from all three has the same characteristic properties. Carbon dioxide is the common oxide of carbon. A lower oxide exists, but on burning it is converted into the dioxide. Wherever the oxidation of carbon takes place, if there is sufficient oxygen, carbon dioxide, carbonic acid, is formed. This reaction is the one used for the determination of carbon in bodies generally. The dioxide has acid properties and combines with lime and other bases, forming a series of salts called carbonates. The carbon compounds, note other than carbonates which will be subsequently considered, end note, occurring in minerals are generally characterized by their sparing solubility in acids. The diamond is distinguished from other crystals by its hardness, luster, and specific gravity. It may be subjected to a red heat without being apparently affected, but at a higher temperature it slowly burns away. Graphite also burns slowly, but at a lower temperature. The other bodies, coals, shales, etc., differ considerably among themselves in the temperature at which they commence to burn. Some, such as anthracite, burn with little or no flame, but most give off gases which burn with a luminous flame. They deflagrate when sprinkled on fused nitre, forming carbonate of potash. In making this test, the student must remember that sulfur and, in fact, all oxidizable bodies similarly deflagrate, but it is only in the case of carbon compounds that carbonate of potash is formed. Carbon unites with iron and some of the metals to form carbides. Combined carbon of this kind is detected by the odour of the carburetted hydrogen evolved when the metal is treated with hydrochloric acid, for example on dissolving steel in acid. The natural carbon compounds, although speaking generally insoluble in hydrochloric or nitric acids, are more or less attacked by aqua regia. The assayer seldom requires these compounds to be in solution. The presence of organic matter, footnote, for example, soluble organic acids formed by partial oxidation with nitric acid, end footnote, interferes with most of the reactions which are used for the determination of the metals. Consequently, in such cases it should be removed by calcination, unless it is known that its presence will not interfere. When calcination is not admissible, it may be destroyed by heating with strong sulfuric acid and bichromate or permanganate of potash, or by fusion with nitre. Carbon may be separated from other substances by conversion into carbon dioxide by burning. In most cases, substances soluble in acids are first removed, and the insoluble residue dried, weighed, and then calcined or burned in a current of air. The quantity of organic matter may be determined indirectly by the loss the substance undergoes, but it is better to determine the organic carbon by confining the calcination in a tube and collecting and weighing the carbon dioxide formed. Each gram of carbon dioxide is equivalent to 0.2727 gram of carbon. Instead of a current of oxygen or air, oxide of copper may be more conveniently used. The operation is as follows. Take a clean and dry piece of combustion tube, drawn out and closed at one end, as shown in the figure, note figure 70, end note, and about 18 inches long. Reader's note, figure 70 shows a length of glass tubing bent up and tapered to a sealed point at one end, end reader's note. Fit it with a perforated cork connected with a U-tube, note containing freshly fused calcium chloride in coarse grains, end note, and a set of potash bulbs containing a strong solution of potash, note figure 71, end note. Reader's note. Figure 71 shows 3 ovoid glass bulbs, each about half full of liquid. An outlet tube from the top of the first bulb enters the top of the second bulb, ending below the surface of the liquid. A similar tube runs from the second bulb to the third. The top of the first bulb receives an inlet tube, which ends below the surface of its contents. There is a large swelling in the inlet tube before it enters the bulb. An outlet tube, leaving the top of the third bulb, expands into a sphere before its exit tube is bent horizontally with another small bulge, before it opens to the outside. End reader's note. The exit of which last is provided with a small tube containing calcium chloride or a stick of potash. Both the U-tube and bulbs should have a loop of fine wire by which they may be suspended on the hook of the balance for convenience in weighing. They must both be weighed before the combustion is commenced. To prevent absorption of moisture during weighing, etc., the ends are plugged with pieces of tube and glass rod. Fill the combustion tube to a depth of about 8 inches with some copper oxide which has been recently ignited and cooled in a closed vessel. Put in the weighed portion for assay and a little fresh copper oxide, and mix in the tube by means of an iron wire shaped at the end after the manner of a corkscrew. Put in some more oxide of copper and clean the stirrer in it. Close loosely with a plug of recently ignited asbestos, place in the furnace, and connect the U-tube and bulbs in the way shown in the sketch. Note: Figure 72. End note. Reader's note: Figure 72 shows a horizontal stand with a gas pipe running along its base. 24 burners run up from the gas pipe, each with a gas tap. A shelf above the burners holds a series of blocks with the combustion tube running through them from left to right. The sealed raised point of the combustion tube leaves the block at the left end, while a set of potash bulbs followed by a small U-tube are attached to the inlet at the right-hand end of the combustion tube. The U-tube and potash bulbs are suspended from wire loops. End footnote. See that the joints are tight, and then commence the combustion by lighting the burners nearest the U-tube. Make the first 3 or 4 inches red hot, and gradually extend the heat backwards the length of the tube, but avoid too rapid a disengagement of gas. When gas ceases to come off, open the pointed end of the tube and draw a current of dried air through the apparatus. The carbon dioxide is absorbed in the potash bulbs, and their increase in weight multiplied by 0.2727 gives the amount of carbon in the substance taken. The increase in weight in the calcium chloride tube will be due to the water formed by the oxidation of the combined hydrogen. If this last is required, the increase in weight multiplied by 0.111 gives its amount. Coals. The determination of the actual carbon in coals and shales is seldom called for. If required, it would be performed in the way just described. Footnote: for coals and other bodies containing sulphur, chromate of lead should be used instead of oxide of copper, and the temperature should be limited to dull redness. End footnote. The ordinary assay of a sample of coal involves the following determinations: moisture, volatile matter, fixed carbon, ash, and sulphur. These are thus carried out. Determination of moisture. Take 3 grams of the powdered sample and dry in a water bath for an hour or so. The loss is reported as moisture. Coals carry from 1 to 2%. If the drying is carried too far, coals gain a little in weight owing to oxidation, so that it is not advisable to extend it over more than 1 or 2 hours. Determination of volatile matter. This determination is an approximate one, and it is only when working under the same conditions with regard to time, amount of coal taken, and degree of heat used that concordant results can be arrived at. It is a matter of importance whether the coal has been previously dried before heating or not, since a difference of 2% may be got by working on the dried or undried sample. Take 2 grams of the powdered but undried sample of coal, place in a weighed platinum crucible, and support this over a good Bunsen burner by means of a thin platinum wire triangle. The heat is continued until no further quantity of gas comes off and burns at the mouth. This takes only a few minutes. The cover is tightly fitted on, and when cold the crucible is weighed. The loss in weight, after deducting the moisture, gives the volatile matter, and the residue consists of fixed carbon and ash. Determination of ash. The coke produced in the last operation is turned out into a porcelain dish and ignited over a Bunsen burner till the residue is free from particles of carbon. Calcination is hastened by stirring with a platinum wire. The operation may be done in a muffle, but this gives results a few tenths of a percent too low. The dish is cooled in a desiccator and weighed. The increase in weight gives the amount of ash, and the difference between this and the weight of the coke gives the fixed carbon. The assay is reported as follows: moisture at 100 degrees centigrade, blank %, volatile matter, blank %, fixed carbon, blank %, ash, blank %, contains sulfur, blank %. Determination of sulfur. The sulfur exists in the coal partly in organic combination, partly as metallic sulfide, iron pyrites, marcasite, etc., and perhaps as sulfate, so that the sulfur determination must be separately reported, since a portion will go off with the volatile matter, and the remainder would be retained and weighed with the coke. The sulfur is thus determined. Take 1 gram of the coal and mix with 1.5 gram of a mixture of 2 parts of calcined magnesia and 1 part of carbonate of soda, and heat in a platinum crucible for 1 hour, or until oxidation is complete. Turn out the mass and extract it with water and bromine. Filter, acidulate with hydrochloric acid, boil off the bromine, and precipitate with baric chloride. Note: estimating gravimetrically as given under sulfur. End note. Another method is as follows. Take 1 gram of the coal and drop it gradually from a sheet of notepaper onto 5 grams of fused nitre contained in a platinum dish. Extract with water, acidify with acetic acid, and estimate volumetrically, as described under sulfur. Calorific effect of coals. The heat-giving value of a coal is best expressed in the number of pounds of water previously heated to the boiling point, which it will convert into steam. This is generally termed its evaporative power. It may be determined by means of the colorimeter. Figure 73. Reader's note: Figure 73 shows a wide glass cylinder with a measuring mark about 3/4 of the way up. Inside the glass container, below the level of the mark, is a copper cylinder. It has an outlet tube at the top, with a stopcock above the level of the top of the glass cylinder. There is another copper cylinder nested inside that copper cylinder, supported by springs at its sides. End reader's note. This consists of a glass cylinder marked to hold 29.010 grains of water. The instrument consists of a perforated copper stand provided with a socket and 3 springs. The socket holds a copper cylinder which is charged with 30 grains of the dried coal mixed with 300 grains of a mixture of 3 parts of potassium chlorate and 1 part of nitre. The charge is well packed in the cylinder and provided with a small fuse of cotton saturated with nitre. Fill the glass cylinder to its mark with water and take the temperature with a thermometer marked in degrees Fahrenheit. Ignite the fuse and immediately cover with the outer copper cylinder, extinguisher fashion, which will be held in its place by the springs. The stopcock should be closed before this is done. Place the apparatus quickly in the cylinder of water. When the action is over, open the stopcock and agitate the water by raising and lowering the instrument a few times. Again, take the temperature. The rise in temperature, plus 10% for the heat used in warming the apparatus and lost by radiation, gives the evaporative power. The following is an example. Temperature before experiment, 67.0 degrees Fahrenheit. Temperature after experiment, 79.0 degrees Fahrenheit. Rise, 12.0 degrees Fahrenheit, plus 1/10, 1.2 degrees Fahrenheit, gives 13.2 degrees Fahrenheit. 1 pound of the coal will evaporate 13.2 pounds of water. Shales, etc. The assay of these is carried out in the same way as that of coals, but the volatile matters are separately examined, and in consequence a larger quantity of material must be used. For the moisture, volatile matter, fixed carbon, and ash, the determinations are the same, but a special distillation must be made to obtain a sufficient quantity of the volatile products for subsequent examination. Take 500 or 1000 grams of the well sampled and powdered shale and introduce into a cast iron retort, as shown in Figure 74. Reader's note: Figure 74 shows a retort with a long outlet tube. The body of the retort is composed of a short cylinder with a convex domed base. A lid leading into its outlet tube is bolted onto the top of the body of the retort. End reader's note. Lute the joint with fire clay, place the cover on, and bolt it down. The bolts should have a covering of fire clay to protect them from the action of the fire. Place the retort in a wind furnace, supporting it on a brick, and pack well round with coke. Build up the furnace around and over the retort with loose fire bricks, and heat gradually. As soon as water begins to drip, the tube of the retort is cooled by wrapping a wet cloth around it and keeping wet with water. The water is kept from running into the receiver by a ring of damp fire clay. A quantity of gas first comes over and will be lost. Afterwards, water and oily matters. The retort must be red hot at the close of the distillation, and when nothing more distills off, which occurs in about 2 or 3 hours, the wet cloth is removed and the tube heated with a Bunsen burner to drive forward the matter condensed in it into the receiver, and thus to clean the tube. It can be seen when the tube is clean by looking up through it into the red-hot retort. The receiver is then removed, and the retort, taken from the furnace, is allowed to cool. When cold, it is opened, and the fixed carbon and ash weighed as a check on the smaller assay. The distillate of water and oil is warmed, and will separate into 2 layers, the upper one of which is oil and the lower water. These are measured, and if the specific gravity of the oil is taken, its weight may be calculated. If the 2 liquids do not separate well, the water may be filtered off after cooling through a damped filter. The separation is, however, best effected in a separator. Note Figure 75. End note. Reader's note: Figure 75 shows a glass separator. It comprises a wide glass cylinder tapering to a narrow tube at its base, closed by a stopcock. Its top is closed off by a glass stopper. End reader's note. The liquids are poured into this, allowed to settle, and the lower layer drained off. The volume of the water is measured and its weight calculated in percents on the amount of shale taken. Examination of the oil. A sufficient quantity of the oil must be got, so that if one distillation does not yield enough, the requisite quantity must be obtained by making 2 or more distillations. The oils are mixed, and the mixture, after having had its volume and specific gravity ascertained, is placed in a copper retort and redistilled with the aid of a current of steam. The residue in the retort is coke. The distillate is separated from the water by means of the separator, and shaken for 10 minutes with 1/20th of its bulk of sulphuric acid. Note specific gravity 1.70. End note. The temperature should not be allowed to rise above 40 degrees. Allowed to stand and run off the acid tar. The oil is now shaken up with from 10 cc to 20 cc of sodic hydrate solution. Note specific gravity 1.3. Allowed to stand, warmed for half an hour, and the soda tar run off. On mixing this soda tar with dilute acid, the crude shale oil creosote separates and is measured off. The purified oil is next redistilled in fractions, which come over in the following order: naphtha, light oil, heavy oil, and still bottoms. For the first product, which is only got from certain shales, the receiver is changed when the distillate has a specific gravity of 0.78. For the second product, the process is continued till a drop of the distillate, caught as it falls from the neck of the retort on a cold spatula, shows signs of solidifying. This is crude light oil. The receiver is changed and the heavy oil comes over. Towards the end, a thick brown or yellow viscid product is got. The receiver is again changed and the distillation carried to dryness. The crude light oil is washed cold with 2% of sulphuric acid, concentrated, and afterwards with excess of soda. Thus purified, it is again distilled to dryness, 3 fractions being collected as before. Naphtha, which is added to the main portion and measured, light oil, which is also measured, and heavy oil, which is added to that got in the first distillation. This last is poured into a flat bottom capsule and allowed to cool slowly. The temperature may with advantage be carried below freezing point. The cooled cake is pressed between folds of linen and the paraffin scale detached and weighed. The results may be reported thus: naphtha, specific gravity, blank; light oil, specific gravity, blank; heavy oil, specific gravity, blank; paraffin scale, blank; coke, etc., blank. The results are calculated in percents on the oil taken. Some workers take their fractions at each rise of 50 degrees centigrade. The composition of average shale, as given by Mills, is as follows: specific gravity 1.877, moisture 2.54, gas, volatile matter, water, ammonia, and oil 23.53%, fixed carbon 12.69%, ash 63.74%, total 99.96%. The ash is made up of silica 55.6, ferric oxide 12.2, alumina 22.14, lime 1.5, sulfur 0.9, soluble salts containing 0.92% sulfuric oxide 8.3, total sulfur in shale 1.8%, total sulfur in ash 1.3%. For further information on these assays, and for the assay of petroleums, bitumens, etc., the student is referred to Allen's Commercial Organic Analysis, Volume 2. Determination of organic carbon in a limestone. Take 1 or 2 grams and dissolve with a very slight excess of dilute hydrochloric acid. Evaporate to dryness and determine the carbon in the residue by combustion with copper oxide. Estimation of carbon in a sample of graphite. Note: black lead. End note. Weigh up 1 or 2 grams in a dish and calcine in the muffle till the carbon is burnt off. Weigh the residue and calculate the carbon by difference. Determination of carbon in iron. The carbon exists in 2 states: free, graphite, and combined. The following process estimates the total carbon. The carbon existing as graphite may be separately estimated in another portion by the same process, but using hydrochloric acid to dissolve the iron instead of the copper solution. Weigh up 2 grams of the iron, or a larger quantity if very poor in carbon, and attack it with 30 grams of ammonic cupric chloride dissolved in 100 c.c. of water. Footnote: this may be prepared by dissolving 534 grams of ammonium chloride and 854 grams of crystallized cupric chloride, CuCl2.2H2O, in hot water and crystallizing. End footnote. Let the reaction proceed for a quarter of an hour, and then warm until the iron is dissolved. Allow to settle, and filter through a filtering tube. This is a piece of combustion tube, drawn out and narrowed at one end, as shown in Figure 76. Reader's note: Figure 76 shows a glass tube drawn in at a sharp shoulder to a narrow outlet tube. A clay ball sits on the shoulder where the tube narrows, with 3 thin layers of substance shown resting on the clay ball in the wider part of the tube. End reader's note. The narrow part is blocked with a pea of baked clay, and on this is placed ½ inch of silica sand, previously calcined to remove organic matter, then a small plug of asbestos, and then a ¼ inch of sand. The tube is connected with a pump, working at a gentle pressure, and the solution is filtered through the tube with the aid of a small funnel. Note Figure 77. End note. Reader's note: Figure 77 shows a straight-sided glass jar with a wide mouth. The stopper in the mouth of the jar has an outlet tube which bends to the horizontal, and the stopper is also penetrated by the narrow end of the glass tube described in Figure 76. End reader's note. The residue is washed, first with dilute hydrochloric acid and then with distilled water. The tube is dried by aspirating air through it and gently warming with a Bunsen burner. The tube is then placed in a small combustion furnace and connected with calcium chloride and potash bulbs, as shown in Figure 78. Reader's note: Figure 78 shows a horizontal combustion tube running through a furnace. Its left end, the inlet, is connected to a U-tube with 3 bulbs, which contains a small amount of liquid. The right-hand end, the outlet, is connected to a U-tube and a set of potash bulbs. End reader's note. The potash bulb to the right of the figure must be weighed. A slow stream of air is drawn through the apparatus and the heat gradually raised. In from 30 minutes to 1 hour the combustion will be complete. The potash bulbs are then disconnected and weighed, and the increase multiplied by 0.2727 gives the weight of carbon. End of section 44. Section 45 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 18. Silicon, Carbon, Boron. Part 3. Carbonates. Carbon dioxide, which is formed by the complete oxidation of carbon, is a gas with a sweetish odour and taste, having a strong affinity for alkalis, and forming a series of compounds termed carbonates. The gas itself occurs in nature and is sometimes met with in quantity in mining. The carbonates occur largely in nature, forming mountain masses of limestone, etc. Carbonates of many of the metals, such as carbonate of lead, cerussite, carbonate of iron, chalybeate, carbonates of copper, malachite and chessylite, and carbonate of magnesia, magnesite, are common. All the carbonates, note those of the alkalis and alkaline earths excepted, end note, are completely decomposed on ignition into the oxide of the metal and carbon dioxide, but the temperature required for this decomposition varies with the nature of the base. All carbonates are soluble with effervescence in dilute acids. Some, such as chalybeate and magnesite, require the aid of heat. The alkaline carbonates are soluble in water. The rest, with the exception of the bicarbonates, are insoluble therein. Carbonates are recognized by their effervescence with acids. A stream of bubbles of gas are given off, which collect in the tube and possess the property of extinguishing a lighted match. The most characteristic test for the gas is a white precipitate, which is produced by passing it into lime or baryta water, or into a solution of subacetate of lead. The expulsion of carbon dioxide by the stronger acids serves for the separation of this body from the other acids and bases. Dry assay. There is no dry assay in use. Any method which may be adopted will necessarily be applicable only to special compounds. Wet methods. There are several methods in use which leave little to be desired either in speed or accuracy. We will give 1. A gravimetric method in which the estimation may be made directly by weighing the carbonic acid, or indirectly by estimating the carbon dioxide from the loss. 2. A volumetric one, by which an indirect determination is made of the gas. And 3. A gasometric method, in which the volume of carbon dioxide given off is measured and its weight deducted. Direct gravimetric method. Fill up the apparatus shown in the diagram. Note Figure 79, end note. Reader's note. Figure 79 shows a round-bottomed flask supported on a stand. A horizontal bar holds a line of U-tubes level with the flask, 1 U-tube to the flask's left and 5 to its right. The 5 U-tubes are connected in series by rubber tubing. The U-tube to the immediate right of the flask, connected to the flask's outlet, is expanded into a bulb in each arm to prevent reflux of the liquid in it. The rightmost U-tube is connected to the top of a large aspirator bottle. This bottle has an outlet tap at its base and is filled with water, so running the water out will draw air through the whole apparatus. There is a small amount of liquid in the flask. The lower stem of a bulb pipette passes through the flask's stopper to below the liquid's surface. A rubber tube connects the mouth of the pipette to the U-tube to the flask's left. End reader's note. The various tubes are supported by a fixed rod with nails and wire loops, and connected by short lengths of rubber tubing. The first tube contains soda lime. The small flask is fitted with a rubber stopper perforated with 2 holes, through one of which passes the tube of a pipette holding 25 or 30 cc. This pipette is to contain the acid. The substance to be determined is weighed out into the flask. The second tube contains strong sulfuric acid. The third, pumice stone, saturated with copper sulfate solution and dried until nearly white at 200 degrees centigrade. The fourth contains recently fused calcium chloride, and the fifth, which is the weighed tube in which the carbonic acid is absorbed, contains calcium chloride and soda lime, as shown in Figure 80. Reader's note: Figure 80 shows 2 U-tubes suspended from wire loops. Inlet and outlet tubes pass through the stoppers at the top of the arms of the U-tubes. End reader's note. Footnote: Soda lime is made by dissolving 100 grams of soda in water and carefully slaking 200 grams of lime with it. Evaporate to dryness in an iron dish and ignite at a low red heat in a crucible. Use the small lumps. End footnote. The sixth also contains calcium chloride and soda lime. Its object is to prevent the access of moisture and carbonic acid to the weighed tube from this direction. It is connected with an aspirator. Having weighed the U-tube and got the apparatus in order, weigh up 1, 2, or 5 grams of the substance and place in the flask. Fill the pipette with dilute acid, close the clamp, and cork the flask. Then see that the apparatus is tight. Open the clamp and allow from 10 to 20 cc of the acid to run onto the assay. Carbonic acid will be evolved and will be driven through the tubes. The gas should bubble through the sulfuric acid in a moderate and regular stream. When the effervescence slackens, the clamp is opened and the greater part of the remaining acid run in. When the effervescence has ceased, the clamp is opened to its full extent and a current of air drawn through with an aspirator. A gentle heat is applied to the flask, but it should not be prolonged or carried to boiling. After the removal of the heat, a gentle current of air is drawn through the apparatus for 30 or 40 minutes. The weighed U-tube, which in the early part of the operation will have become warm if much carbonic acid was present, will by this time be cold. It is disconnected, plugged, and weighed. The increase in weight is due to carbon dioxide of the sample. Example: ore taken 1 gram, weight of tube before 42.6525 grams, weight of tube after 43.0940 grams. Increase equals carbon dioxide 0.4415 grams. Indirect gravimetric, or determination by loss. Take a Geissler's carbonic acid apparatus, note Figure 81, end note, and place in the double bulb some strong sulfuric acid. Reader's note: Figure 81 shows a glass flask whose main body is wider than it is tall. The flask has 3 necks. That on the right, labelled A, has a glass stopper. The stopper of the middle neck is penetrated by a glass tube that reaches almost to the bottom of the flask. A stoppered bulb leads into the top of this glass tube. There is a stopcock at the bottom of the bulb. The left neck of the flask leads into a complex double glass bulb, stoppered at its top. End reader's note. Put in the other bulb, the stopcock being closed, 3 or 4 cc of nitric acid diluted with water. Leave the apparatus in the balance box for a few minutes and weigh. Introduce into the flask, note through A, end note, about 1 gram of the powdered substance, and again weigh to find the exact amount added. Allow the acid to run gradually onto the carbonate, and when solution is complete, heat and aspirate. Cool and again weigh. The loss in weight is the carbonic acid. For example, weight of apparatus and acids 85.494 grams, weight of apparatus and marble 86.879 grams, equal to marble taken 1.385 grams. Weight of apparatus and marble 86.879 grams. Weight of apparatus and marble 86.879 grams. Weight of apparatus minus carbonic acid 86.2692 grams, equal to carbonic acid 0.6098 grams. 1.385 to 100 is equivalent to 0.6098 to X. X equals 44.03%. The substance contains 44.03% of carbonic acid. A duplicate experiment gave 43.73%. This method is quicker but less exact than the direct gravimetric determination. Volumetric method. This, which is of somewhat limited application, is based upon the determination of the quantity of acid required to decompose the carbonate. It consists in adding to a weighed quantity of the mineral a known amount of standard solution of acid, which is in excess of that required to effect the decomposition. The quantity of residual acid is then determined by titrating with standard solution of alkali. This method has been described under lime. Gasometric method. This method is the quickest of all, and the least troublesome after the apparatus has been once prepared. It yields fairly accurate results when worked in the manner described below, but if greater precautions are taken, the results are exact. It depends on the measurement of the volume of gas given off on treating the weighed sample with acid. The apparatus described, page 52, is used. Reader's note, figure 30 in the section on weighing and measuring. End reader's note. Weigh out a portion of the mineral, which shall contain not more than 0.15 gram of carbonic acid, note, or 0.4 gram of carbonate of lime, end note, and put it in the bottle. Put in the inner tube 10 cc of dilute hydrochloric acid, note 1 to 1, end note. Cork tightly and read off the level of the liquid in the burette after adjusting the pressure. Turn the acid over onto the mineral. Run out the water so as to keep the level in the two burettes the same. When effervescence has ceased, rotate the contents of the bottle. Finally, adjust the level in the burettes and read off the volume. The increase in volume is due to the evolved carbon dioxide. At the same time, read off the volume corrector. Some of the carbon dioxide remains dissolved in the acid in the generating bottle, and the quantity thus dissolved will depend on the amount of carbonate as well as on the amount of acid present. Consequently, a measured quantity of acid should be used in each assay, and a comparative experiment made with a known weight of pure carbonate of lime, which will yield about the same volume of gas. The number of cc's of gas got in the assay multiplied by 4.7 will give the number of milligrams of pure carbonate of lime that must be taken for the standard. With ordinary work, the error rarely exceeds half a cc. The following example will illustrate the calculations. 1 gram of a mineral was taken and yielded 49.0 cc of gas. The volume corrector reading was 100.4 cc. 0.2405 gram of pure carbonate of lime was then taken and treated in the same way. 50.5 cc of gas were got. The volume corrector still read 100.4 cc. 0.2405 gram of carbonate of lime is equivalent to 0.1058 gram of carbon dioxide. Then 50.5 to 49.0 is equivalent to 0.1058 to X. X equals 10.26%. Estimation of carbonic acid in the air of mines. According to a series of analyses by Angus Smith, the proportion of carbonic acid in the air of underground workings varied from 0.04 to 2.7% by volume. In places where men are working, the proportion ought not to reach 0.25%. A simple method of determining whether a sample of air reaches this limit, 0.25%, is described by Dr. C. Leneve Foster In the Proceedings of the Mining Association and Institute of Cornwall for 1888, the apparatus used is an ordinary corked 8-ounce medicine bottle. This is filled with the air to be examined by sucking out its contents with a piece of rubber tube. Half an ounce of dilute lime water, footnote, made by diluting 1 part by measure of saturated lime water up to 10 with recently boiled distilled water, end footnote. Tinted with phenolphthalein, is poured in. If, on corking the bottle and shaking, the colour is not discharged, the air contains less than 0.25% of carbon dioxide. If the colour fades slowly and does not finally vanish till after a great deal of shaking, it may be assumed that the percentage of carbon dioxide does not greatly exceed 1/4. Whereas if the disappearance is rapid after a very few shakes, the contrary, of course, is the case. The diluted lime water is measured out and carried in ordinary half-ounce phials. This method does not pretend to great accuracy, but as a method of distinguishing between good and bad air, it is very convenient and will be found useful. For determining the actual proportion in the air, the following plan is adopted. Take a bottle which will hold about 50 ounces and measure its capacity. Fill the bottle with the air to be examined. Pour in 100 cc of lime water and shake up for some time. Add phenolphthalein and titrate the remaining calcium hydrate with standard solution of oxalic acid. The solution of oxalic acid is made by dissolving 2.25 grams of recrystallized oxalic acid, note H2C2O4.2H2O, end note, in water and diluting to 1 litre. 1 cc equals 0.001 gram of lime, CaO, or 0.0007857 gram of carbon dioxide. Take 100 cc of the same lime water, to which add the same amount of phenolphthalein as before. Titrate. The difference between the two readings gives the amount of acid equivalent to the lime water neutralized by the carbon dioxide. The number of cc's thus used up, when multiplied by 0.3989, gives the number of cc's of carbon dioxide at 0 degrees centigrade and 760 millimeters in the volume of air taken. This volume, which is that of the bottle less 100 cc's, must, in accurate work, be reduced to the normal temperature and pressure. Footnote. See under gasometric assays. End footnote. The percentage by volume can then be calculated. Practical exercises. 1. In a gasometric determination, 71.3 cc's of gas were obtained from 0.2055 gram of mineral. The volume corrector reading was 102.2 cc's. 0.3445 gram of pure carbonate of lime gave 74.1 cc's. The volume corrector reading was 100.6. What is the percentage of carbon dioxide in the substance? 2. What volume of dry gas at 0 degrees centigrade and 760 millimeters pressure should be obtained from 0.3445 gram of carbonate of lime? 1 cc of CO2 under these conditions weighs 1.97 milligrams. 3. A sample of coal is reported on as follows: specific gravity 1.315, moisture 1.001, volatile matter 35.484, fixed carbon 50.172, ash 12.028, total 100.000. What is there about this requiring explanation? 4. Calculate the percentage of carbonic acid in a mineral from the following data. Weight of apparatus and acids 87.0888 grams. Weight of apparatus and acids plus mineral 88.8858 grams. Weight of apparatus and acids after loss of carbonic acid 88.1000 grams. 5. A sample of pig iron contains 1.43% of combined and 2.02% of free carbon. Taking 2 grams of it for each determination, what weight of CO2 will be got on burning the residue from solution in ammonium cupric chloride, and what from the residue after solution in hydrochloric acid? Boron and borates. Boron occurs in nature as boric acid or sacchaline, H3BO3, borax or tincal, note Na2B4O7.10H2O, end note, ulexite or boronatrocalcite, note 2CaB4O7.Na2B4O7, end note, borocalcite, note CaB4O7.4H2O, end note, borosite, note 2Mg3B8O15.MgCl2, note, and some other minerals. Boric acid is also a constituent of certain silicates, such as tourmaline, axinite, and datholite. The natural borates are used in the preparation of borax, which is largely employed as a preservative agent, for fluxing, and for other purposes. There is only one series of boron compounds which have any importance. These are the borates, in which the trioxide, B2O3, acts the part of a weak acid. The addition of any acid liberates boric acid, which separates out in cold solutions as a crystalline precipitate. Boric acid is soluble in alcohol and in hot water. On evaporating these solutions it is volatilized, although the anhydrous oxide is fixed at a red heat. The borates are mostly fusible compounds and are soluble in acids and in solutions of ammonic salts. Detection. Boron in small quantities will escape detection unless specially looked for, but there is no difficulty in detecting its presence. Heated in the Bunsen burner flame with Turner's test, it gives an evanescent yellowish-green colour due to fluoride of boron, Bf3. Turner's test is a mixture of 5 parts of bisulfate of potash and 1 part of fluorspar. Boric acid itself imparts a characteristic green colour to the flame, which gives a spectrum made up of 4 well-marked and equidistant lines, 3 in the green and 1 in the blue. Solutions of boric acid give, with turmeric paper which has been dipped into it and dried, a characteristic red tint. This is a very delicate test, but in trying it, a blank experiment should be carried out alongside with a solution made up of the same reagents which have been used in liberating the boric acid in the sample. Solution and separation. The solution presents no difficulty, but the separation is troublesome. The best method is that of Gooch, who, if necessary, first fuses with carbonate of soda, and after the removal of chlorides and fluorides, note by nitrate of silver or a lime salt, end note, evaporates the aqueous extract with nitric or acetic acid to dryness in a retort, and subsequently with repeated doses of 10 cc each of methyl alcohol. The distillate contains the boron as boric acid. Half a gram of the trioxide, B2O3, is completely carried over by 2 evaporations, each with 10 cc of the alcohol, but if water or foreign salts are present, more than this is required. In ordinary cases, 6 such evaporations are sufficient for 0.2 gram of the oxide. Footnote: see A Method for the Separation and Estimation of Boric Acid by F. A. Gooch. Chemical News, January 7th, 1887. End footnote. Gravimetric determination. Before the introduction of Gooch's process, it was usual to determine the boron trioxide by difference. If the alcoholic distillate containing the boric acid is digested with about 1 gram, a known weight, of lime for 10 or 15 minutes, the alcohol can be evaporated off without danger of loss. Either calcium nitrate or acetate, which will be formed at the same time, yields lime upon subsequent ignition. Consequently, the increase in weight after ignition upon that of the lime taken gives the amount of boron trioxide present. The trioxide contains 31.4% of boron, note B, end note. Since magnesia does not form a soluble hydrate, it cannot satisfactorily be used instead of lime. The apparatus required is shown in Figure 82. Reader's note: Figure 82 shows a Bunsen burner and tripod standing on a large block. A wide-mouthed bowl, the paraffin bath, rests on the tripod. The body of a large bulb pipette is suspended horizontally above the bowl. The ends of the pipette are bent upwards. The right end has a small funnel running into it. The left end of the pipette is bent over until it enters the top of a vertical water-cooled condenser. The outlet from the condenser runs into a small conical flask that rests on the bench top next to the block holding the paraffin bath. End reader's note. It consists of a small retort or evaporating vessel made out of a pipette of 200 cc capacity. This is heated by means of a paraffin bath at 130 degrees or 140 degrees centigrade. It is connected with an upright condenser, at the lower end of which is a small flask which serves as a receiver. The quantity of the borate taken should contain not more than 0.2 gram of the trioxide. Insoluble compounds are dissolved in nitric acid at once, or, if necessary, first fused with sodium carbonate. With soluble and alkaline borates, sufficient nitric acid is added to render it faintly acid. The solution is then introduced into the retort. The lime, to retain the boric acid in the distillate, is ignited in the crucible in which the evaporation of the distillate is to be made subsequently. It is then cooled in the desiccator for 10 minutes and weighed. The lime is transferred to the receiving flask and slaked with a little water. The retort is lowered into the bath so that only the rear dips below the surface. The evaporation is carried to dryness, the retort being lowered further into the bath as the evaporation proceeds. 10 cc of methyl alcohol are introduced upon the residue, and the evaporation again started. 6 such portions of alcohol are thus distilled, and 2 cc of water are introduced and evaporated between the second and third, as also between the fourth and fifth distillations. If acetic acid is used instead of nitric in the first instance, this addition of water is unnecessary. The distillate is evaporated in the crucible, ignited over the blowpipe, cooled in the desiccator for 10 minutes, and weighed. The increase in weight gives the boron trioxide. The results tend to be from 1 to 2 milligrams too high. Volumetric method. This method is applicable to the indirect determination of boric acid in borax and similar compounds. It is based on the measurement of the quantity of normal solution of acid required to replace the boric acid, and consequently is rather a measure of the soda present. The process is an alkalimetric one, and is carried out as follows. Weigh up 3 grams of the sample and dissolve in water. Tint with methyl orange, and run in from an ordinary burette normal solution of sulfuric acid until a pink tint is got. 100 cc of the normal solution of acid are equal to 7.0 grams of boron trioxide, B2O3, or 10.1 grams of anhydrous borax, Na2B4O7. Examination of borax. In addition to the determination just given, the following determinations are also required. Water. Take about 2 grams and heat to tranquil fusion in a platinum crucible. Count the loss in weight as water. Sulfuric oxide. Take 2 grams, dissolve in water, acidify with hydrochloric acid, filter, and precipitate with barium chloride. Wash the precipitate, ignite, and weigh as barium sulfate. Note: see sulfur. End note. Chlorine. Take 2 grams, dissolve in water, acidify with nitric acid, filter, and add silver nitrate. Collect, wash, and weigh the precipitate as silver chloride. Alumina. Take 5 or 10 grams, dissolve in water, boil, add ammonia in slight excess, and filter off the precipitate when it has settled. Wash with hot water, ignite, and weigh as alumina, Al2O3. End of section 45. Section 46 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Reader's note: Appendix A has been omitted. It consists of a table of atomic weights and other constants, table for converting degrees centigrade into degrees Fahrenheit, tables for showing percentage by weight of the substances in aqueous solutions of different specific gravities at 15 degrees centigrade. End reader's note. Appendix B. Estimation of small quantities of gold. Footnote. For fuller information, see a paper on The Estimation of Minute Quantities of Gold by Dr. George Tate, read before the Liverpool Polytechnic Society, November 1889. End footnote. In the case of small buttons of gold, the weight can be determined more easily and accurately by measuring with the help of a microscope than by the actual use of a balance. Moreover, the method of measurement is applicable to the determination of quantities of gold too minute to affect even the most delicate balance. For quantities of gold from 0.5 to 0.005 mg, a microscope with half-inch objective and B eyepiece is suitable. The measurements are made with the help of a scale engraved, or better, photographed, on a circular piece of glass which rests on the diaphragm of the eyepiece. This scale and the object upon the stage can be easily brought into focus at the same time. The button of gold obtained by cupelling is loosened from the cupel by gently touching with the moistened point of a knife. It generally adheres to the knife and is then transferred to a glass slide. The slide is placed on the stage of the microscope, illuminated from below, and the button is brought into focus and so placed that it apparently coincides with the scale. The diameter in 2 or 3 directions, avoiding the flattened surface, are then read off, the different directions being got by rotating the eyepiece. The mean diameter is taken. The weight of the button is arrived at by comparing with the mean diameter of a standard prill of gold of known weight. The weights are in the proportion of the cubes of the diameters. For example, suppose a prill has been obtained which measures 12.5 divisions of the scale, and that a standard prill weighing 0.1 mg measures 11.1 divisions. The weight will be calculated as follows. 11.1 cubed to 12.5 cubed is equivalent to 0.1 to x. X equals 0.1 times 12.5 times 12.5 times 12.5, all divided by 11.1 times 11.1 times 11.1, equaling 0.143 mg. The calculations are simplified by the use of a table of cubes. The standard prills used in the comparison should not differ much in size from the prills to be determined. They are prepared by alloying known weights of gold and lead so as to get an alloy of known composition, say 1% gold. Portions of the alloy containing the weight of gold required, say 0.1 mg, are then weighed off and cupelled on small smooth cupels made with the finest bone ash. Care must be taken to remove the cupels as soon as cupellation has finished. Several standard prills of the same size should be made at the same time, and their mean diameter calculated. The lead for making the gold-lead alloy is prepared from litharge purified by reducing from it about 10% of its lead by fusion with a suitable proportion of flour. The purified litharge is powdered, mixed with sufficient flour, and reduced to metal. In determining the gold contained in small buttons of silver-gold alloy obtained in assaying, note, and in which the silver is almost sure to be in excess of that required for parting, end note, transfer the button from the cupel to a small clean porcelain crucible. Pour on it a drop or two of nitric acid, diluted with half its bulk of water, and heat gently and cautiously until action has ceased. If the residual gold is broken up, move the crucible so as to bring the particles together so that they may cohere. Wash 3 or 4 times with distilled water, about half filling the crucible each time and decanting off against the finger. Dry the crucible in a warm place and when dry, but whilst still black, take the gold up on a small piece of pure lead. Half a grain of lead is sufficient, and it is best to hold it on the point of a blunt penknife and press it on the gold in the crucible. The latter generally adheres. Transfer to a small smooth cupel and place in the muffle. When the cupellation has finished, the button of gold is measured as already described. Practical notes on the iodide process of copper assaying. For the following remarks and experiments we are indebted to Mr. J. W. Westmoreland, who has had considerable experience with the process. Having dissolved the ore, he converts the metals into sulfates by evaporating with sulfuric acid. The copper is then separated as subsulfide by means of hyposulfite of soda, and the precipitate is washed, dried, and calcined. The resulting oxide of copper is then dissolved in nitric acid, and to the concentrated solution a saturated solution of carbonate of soda is added in sufficient quantity to throw down a considerable proportion of the copper. Acetic acid is added to dissolve the precipitate, and when this is effected, more of the acid is poured on so as to render the solution strongly acid. To this, potassium iodide crystals are added in the proportion of 10 parts of iodide to each 1 part of copper supposed to be present. The solution is then titrated with hypo as usual. For the examination of technical products, experiments made in sulfuric acid solutions have no value, since arsenic acid, which is generally present to a greater or less extent, affects the end reaction. In such solutions, bismuth may also interfere. The solution best suited for the assay is one containing acetate of soda and free acetic acid. The presence of acetate of soda counteracts the interference of arsenic and of bismuth. The return of the blue colour after titration is due to the excessive dilution of the assay, or to an insufficiency of potassium iodide, or to the presence of nitrous fumes. The interference of an excess of sodium acetate is avoided by adding more iodide crystals to the extent of doubling the usual amount. The interference of lead can be avoided by the addition of sulfuric acid or of phosphate of soda to the acid solution containing the copper, and before neutralizing with carbonate of soda. The end reaction is, however, with care, distinguishable without this addition. The following experiments, each containing 0.0648 gram of lead in illustration. Copper taken, 0.2092 gram. Reagent added, none. Copper found, 0.2077 gram. End reaction, fairly satisfactory. Copper taken, 0.2101 gram. Reagent added, none. Copper found, 0.2092 gram. End reaction, fairly satisfactory. Copper taken, 0.2167 gram. Reagent added, sulfuric acid. Copper found, 0.2152 gram. End reaction, fairly satisfactory. Copper taken, 0.2117 gram. Reagent added, sulfuric acid. Copper found, 0.2108 gram. End reaction, fairly satisfactory. Copper taken, 0.2109 gram. Reagent added, phosphate of soda. Copper found, 0.2092 gram. End reaction, good, colourless. Copper taken, 0.2205 gram. Reagent added, phosphate of soda. Copper found, 0.2174 gram. End reaction, rather yellow. Effect of sodium acetate. Each solution contained 0.3343 gram of copper. A, B, and C, acetate added 0 grams. Iodide added 3.5 grams. Copper found 0.3343 grams. D, acetate added 16.2 grams. Iodide added 3.5 grams. Copper found 0.3324 grams. E, acetate added 16.2 grams. Iodide added 7.0 grams. Copper found 0.3351 grams. F, acetate added 16.2 grams. Iodide added 3.5 grams. Copper found 0.3269 grams. G. Acetate added 16.2 grams, iodide added 7.0 grams, copper found 0.3356 grams. In these experiments, except with the excessive quantities of acetate of soda and the insufficiency of potassium iodide in the cases of D and F, there was no difficulty with the after bluing. Method of separating cobalt and nickel. The following method of separating and estimating cobalt and nickel has been described by Mr. James Hope, footnote, Journal of the Society of Chemical Industry, No. 4, Volume 9, April 30th, 1890, end footnote, with whom it has been in daily use for several years with completely satisfactory results. The quantity of ore taken should contain about 0.5 gram of the mixed metals. It is dissolved in hydrochloric acid or aqua regia, and the solution evaporated to dryness. The residue is taken up with dilute hydrochloric acid and hot water. The solution is filtered off from the silica, freed from the second group metals by treatment with sulphuretted hydrogen, and filtered, and after oxidation with nitric acid is separated from iron and alumina by the basic acetate method. Note page 233, end note. Reader's note in chapter 11 in the section on iron, end reader's note. The precipitate is redissolved in a little hydrochloric acid and again precipitated by sodium acetate. The two filtrates are mixed and treated with a little acetic acid, and the cobalt and nickel are then precipitated as sulfides by a current of sulphuretted hydrogen. The precipitate is filtered off, washed, dried, and calcined, and the resulting oxides are weighed to get an idea as to the quantity of the two metals present. The calcined precipitate is dissolved in a small covered beaker in aqua regia with the help of a few drops of bromine to remove any separated sulfur, and the solution evaporated to dryness with a few drops of sulfuric acid. The residue is dissolved in hot water, diluted to about 50 cc and heated to boiling. About 2 grams, note 4 times the quantity of mixed metals present, end note, of ammonium phosphate, AmH2PO4, are weighed off, dissolved in the smallest possible quantity of water, and boiled for a minute or two with a few cc's of dilute sulfuric acid. This is added to the boiling hot solution of cobalt and nickel, which is then treated cautiously with dilute ammonia until the precipitate partially dissolves. The addition of the ammonia is continued drop by drop with constant stirring until the cobalt comes down as a pink precipitate of ammonium cobalt phosphate, AmCoPO4. The beaker is placed on the top of a water bath with occasional stirring for 5 or 10 minutes. The blue liquid containing the nickel is decanted through a small filter, and the precipitate is dissolved with a few drops of dilute sulfuric acid. The resulting solution is treated with a small excess of ammonium phosphate, and the cobalt again precipitated by the cautious addition of ammonia, exactly as before. The precipitate containing the whole of the cobalt is filtered off and washed with small quantities of hot water. The filtrate is added to the previous one containing the greater part of the nickel. The ammonium cobalt phosphate is dried, transferred to a platinum crucible, and ignited over a Bunsen flame for 15 or 20 minutes. A purple-coloured cobalt pyrophosphate, CO2P2O7, is thus formed and is weighed. It contains 40.3% of cobalt. The mixed filtrates containing the nickel are placed in a tall beaker and diluted if necessary to about 200 cc. 10 cc of strong ammonia are added, and the solution, heated to 70 degrees centigrade, is ready for electrolysis. A battery of 2 1.5 pint Bunsen cells is used. This is found capable of depositing from 0.15 to 0.20 gram of nickel per hour, and from 2 to 3 hours is generally sufficient for the electrolysis. The electrode with the deposited nickel is washed with distilled water, afterwards with alcohol, as described under copper, and is then dried and weighed. The following results obtained with this method by Mr. Hope illustrate the accuracy of the method. They were obtained by working on solutions containing known weights of the two metals. Taken 0.1236 gram cobalt, 0.1155 gram nickel. Found 0.1242 gram cobalt, 0.1155 gram nickel. Taken 0.1236 gram cobalt, 0.0577 gram nickel. Found 0.1232 gram cobalt, 0.0575 gram nickel. Taken 0.2472 gram cobalt, 0.0577 gram nickel. Found 0.2449 gram cobalt, 0.0585 gram nickel. Taken 0.3708 gram cobalt, 0.0577 gram nickel. Found 0.3701 gram cobalt, 0.0580 gram nickel. Taken 0.0618 gram cobalt, 0.3465 gram nickel. Found 0.0619 gram cobalt, 0.3454 gram nickel. Taken 0.0618 gram cobalt, 0.2310 gram nickel. Found 0.0625 gram cobalt, 0.2295 gram nickel. Taken 0.0618 gram cobalt, 0.1155 gram nickel. Found 0.0621 gram cobalt, 0.1155 gram nickel. End of section 46. Section 47 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Appendix C. A lecture on the theory of sampling. The problem of the sampler is essentially the same as that of the student of statistics. One aims at getting a small parcel of ore, the other a number of data, but each hopes to obtain what shall represent a true average applicable to a much larger mass of material. Ignoring the mechanical part of the problems, the sampling errors of the one and the deviations from the average of the other are the same thing. It may be doubted whether many not specially trained in the study of statistics could answer such a question as the following. 700,000 men being employed, there are, in a given year, 1,000 deaths from accident. Assuming the conditions to remain unaltered, within what limits could one foretell the number of deaths by accident in any other year? On the other hand, there is a widespread belief in the efficacy of what is called the law of averages. Even the ordinary newspaper reader is accustomed to look on the national death rate or birth rate as a thing capable of being stated with accuracy to 1 or 2 places of decimals, and he knows that the average number of suicides is practically constant. If a man played whist often and kept a record of the number of trumps in each hand, he would find fortune treated him quite fairly. In a year's play, the average number would deviate very little from the theoretical average, i.e. 1/4 of 13. And a knowledge of this truth is useful, and that not merely in keeping ejaculations in due restraint. But every good player knows more than this. He has a sense of what variations in the number of trumps may reasonably be expected. For example, he will be prepared to risk something on neither of his opponents having more than 5 trumps, and will accept it as a practical certainty that no one has more than 8. Much of what is known as good judgment is based on a proper estimate of deviations from the average. The question has an important bearing on sampling, as may be seen from the fact that shuffling and dealing at cards are but modifications of the well-known mixing and quartering of the sampler. Because of this bearing on sampling, and for other reasons, I became many years ago much interested in the question, and gave to its solution perhaps more labour than it was worth. In books on medical statistics, the answer to the question is stated in a mathematical formula called Poisson's formula, which, in a modified form, I shall give further on. But this did not satisfy me, because I wanted to learn what a reasonably safe limit of error actually meant, and this could be best learnt by experiment. So, with the help of some friends, I went in for a thorough course of penny tossing. Tossing a penny 20 times, an average result would be 10 heads and 10 tails. To find the deviations from this, we tossed 200 20s, i.e. 4,000 times. Of the 200, 33 gave the exact average, that is 10 heads. 64 gave an error of 1, that is 9 or 11 heads. 49 an error of 2, 26 an error of 3, 20 an error of 4, 8 gave an error of 5, and this limit was not exceeded. From these we may say that 6 is a reasonably safe limit of error. 97 cases, say 1/2, gave an error not exceeding 1, and the mean error is 1.8. In other words, in 20 tosses you will not get more than 16, nor less than 4, heads. You are as likely as not to get 9, 10 or 11 heads. And lastly, if you lost in 20 throws all heads or tails over 10, your average loss would be 1.8 pennies, or say roughly twopence on the 20 throws. It was necessary to compare these with another series containing a larger average, say that of 100 heads in 200 throws. I confess the labour of tossing pennies 200 at a time was little to our taste, so from a bag of pennies borrowed from the bank, we weighed out samples containing 200, and for an evening we were busy counting heads and tails in these. The heads in 60 samples ranged from 80 to 114. 100 heads occurred 7 times. The extent and frequency of the errors is shown in the table. Error 1, 8 times. Error 2, 5 times. Error 3, 6 times. Error 4, 3 times. Error 5, 6 times. Error 6, 3 times. Error 7, 3 times. Error 8, 3 times. Error 9, 7 times. Error 10, 1 time. Error 11, 1 time. Error 14, 3 times. Error 15, 1 time. Error 18, 2 times. Error 20, 1 time. We may call the limit of error 21. 29 results out of 60, say 1/2, had an error not exceeding 4, and the mean error is 5.6. In comparing these with the series 10 in 20, we must, working by rule, divide not by 10 but by 3.16, the square root of 10, for if we multiply an average by any number, footnote, the 10 in 20 multiplied by 10 equals 100 in 200, end footnote, the error is also multiplied, but only by the square root of the number. The error varies as the square root of the number. Now, 21 divided by 3.16 equals 6.6, equals the limit of error for 10 in 20. 5.6 divided by 3.16 equals 1.8, equals the mean error for 10 in 20. 4 divided by 3.16 equals 1.2, equals the probable error for 10 in 20. It will be seen that these calculated results agree fairly well with those actually obtained. The rule by which these calculations are made is important and will bear further illustration. To calculate the number of heads in 3,200 throws, we have to find the limit of error on a true average of 1,600 in 3,200. This being 16 times the average of 100 in 200, the corresponding errors must be multiplied by 4. This gives 21 times 4 equals 84, equals limit of error. 5.6 times 4 equals 22.4, equals mean error. 4 times 4 equals 16, equals probable error. The results I have actually obtained with these large numbers are hardly enough to base much on, but have a value by way of confirmation. Expecting 1,600 heads, the actual numbers were 1,560, 1,596, 1,643, 1,557, 1,591, 1,605, 1,615, 1,545. It will be seen that exactly half are within the probable error, but this, considering the small number of results, must be more or less of an accident. It is more to the point that they are all well within the limits of error. I have a large number of other results which, with a single exception, are all in accord with those given, and this exception only just overstepped the limits. It was like a case of 9 trumps, which, though in a sense possible, is very unlikely to happen in anyone's experience. But even now, we are not quite in a position to answer the question with which we started. If you refer to it, you will see that we are face to face with this problem. The limit of variation on the 1,000 who died would be, say, 70, ignoring decimals. Footnote: multiply the errors for 100 by the square root of 10. End footnote. But if we calculate on the number who did not die, that is 699,000, footnote: multiply the errors for 100 by the square root of 6,990, end footnote, we shall get a variation 26 times as great as this, but it is evident the variation must be the same in each case. I submitted this kind of problem also to the test of experiment, the results of which gave me great faith in Poisson's formula. Imagine 200 pennies in a bag, all heads up. Any shaking will spoil this arrangement and give a certain proportion of tails. And further, the probable effect of shaking and turning will be to reduce the preponderance of heads or tails, whichever may be in excess. This, of course, is the reason why we are so unlikely to get more than 120 of them in either position. But if the 200 pennies are increased to 20,000 by adding pennies which have tails on both sides, then the shaking or mixing would be less effective. We should still expect, as an average result, to get the 100 heads, but in 20,000 instead of 200. The variation will be 28 or 29 on the 100 instead of 20, and this is a better limit in such cases. Taking 28 as the limit of error on 100 instances, and proportionately increasing the others, so that the mean error becomes 7.8 and the probable error 5.6, we may now calculate the answer without gross mistake. The probable variation on the 1,000 deaths by accident will be 18, the mean variation will be 24.6, and the limits of variation 88.5. One such table showing in 5 years a mean number of deaths of about 1,120 per annum gives an average deviation of about 50 up or down of this. It will be seen at once that an improvement of 30 or 40 in any 1 year would be without meaning, but that an improvement of from 100 to 200 would indicate some change for the better in the circumstances of the industry. Before applying these principles to the elucidation of some of the problems of sampling, it will be well to give Poisson's formula in a modified form, and to illustrate its working. Let x equal the number of cases of one sort, y the cases of the other sort, and z the total. In the example, z will be the 700,000 engaged in the industry, x will be the 1,000 killed by accidents, and y will be the 699,000 who did not so die. The limits of deviation or error calculated by Poisson's formula will be the square root of 8xy, all divided by z. Replacing x, y, and z by the figures of the example, we get the square root of 8 times 1,000 times 699,000, all divided by 700,000, which works out to be the square root of 7,988.57, or 89.3. Which means that we may reasonably expect the number of deaths not to vary from 1,000 by more than 89, i.e. they will be between 1,090 and 910. It will be seen that this number is in very satisfactory agreement with 88.5, given by the rougher calculation based on my own experiments. To come to the question of sampling, consider a powder of uniform fineness and fine enough to pass through an 80 sieve. For purposes of calculation, this may be assumed to be made up of particles of about 1/8 of a millimetre across, say roughly 1/200th of an inch. Cubed, this gives the content as about 1/500th, strictly 1 divided by 512, of a cubic millimetre. Now 1 cubic millimetre of water weighs 1 milligram. Therefore 500 such particles, if they have the specific gravity of water, weigh 1 milligram, and otherwise weigh 1 milligram multiplied by the specific gravity. 500 particles of ruby silver, pyrargyrite, footnote, specific gravity 5.8, silver 60%, end footnote, will weigh 5.8 milligrams and will contain nearly 3.5 milligrams of silver. Now, suppose a portion of 3.2667 grams, note 1/10 of an assay ton, end note, of silver ore to contain 500 such particles of ruby silver and no other material carrying silver. Such an ore would contain 35 ounces of silver to the ton, but the limits of variation on 500 particles would be 28, footnote, taking 28 as the limit of variation on 100, end footnote, multiplied by the square root of 5, or 62 particles. Thus the limit of sampling error would amount to just 1/8 of the silver present, or say to rather more than 4 ounces to the ton. The mean sampling error would be rather more than 1/4 of this, or say about 1.3 ounces to the ton. On the other hand, if one took for the assay a charge 6 times greater, say about 20 grams, the number of particles would be 3000, and the limits of variation would be 28 multiplied by the square root of 30, or 153 particles, which is very closely 1/20th of the silver present, or say 1.75 ounces to the ton, while the mean error would amount to about 0.5 ounces to the ton. To work these examples by Poisson's formula, let us assume the gangue to have a mean specific gravity of 3. Then 500 particles would weigh 3 milligrams and 3.2609 grams. Footnote, the weight of the ore less the weight of ruby silver in it, end footnote, would contain 543,500 particles. There would be then 500 of ruby silver and 543,500 of gangue, together 544,000, and the formula gives the square root of 8 times 500 times 543,500, all divided by 544,000, which works out to 63 particles as against 62 by the other method. A practical conclusion from this is, of course, that either the ore must be powdered more finely, or a larger portion than 3 grams must be taken for the assay. Moreover, it is evident that on such an ore no small sample must be taken containing less than several million particles. Consider now a copper ore of the same uniform fineness, containing particles of copper pyrites, specific gravity 4, of which 1000 particles will weigh 8 milligrams, mixed with gangue of which 1000 particles weigh 6 milligrams. If 1 gram of such ore contain 0.5 gram of copper pyrites, note equals 0.1725 gram copper, end note, and 0.5 gram of gangue, these will contain 62,500 and, say, 83,500 particles respectively, altogether 146,000 particles. With Poisson's formula, this gives the limit of sampling error as the square root of 8 times 62,500 times 83,500, all divided by 146,000, or 521 particles. But a variation of 521 on 62,500 is a variation of 0.83%. The percentage of copper in the ore is 17.25%, and 0.83% of this is 0.14%. The limits of sampling error, therefore, are 17.11% and 17.39%. Again, it must be remembered that the mean sampling error would be a little over 1/4 of this, or say from 17.2% to 17.3%. The practical conclusion is that a powder of this degree of fineness is not fine enough. In the last place, let us consider a similar iron ore containing 90% of hematite, specific gravity 5, and 10% of gangue, specific gravity 3. 1 gram of such ore will contain 90,000 particles of hematite, weighing 0.9 gram, and containing 0.63 gram of iron, with, say, 16,500 particles of gangue, weighing 0.1 gram. Altogether, 106,500 particles. Poisson's formula then gives the limits of variation as the square root of 8 times 90,000 times 16,500, all divided by 106,500, or 334 particles. But 334 on 90,000 is 0.23 on 63.0, which is the percentage of iron present. The limits of sampling error, then, are 62.77% and 63.23%, and the mean variation is from 62.94% to 63.06%. These examples are worthy of careful consideration, and it must be remembered that the calculations are made on the assumption that the ore is made up of uniform particles of mineral of such fineness as would pass easily through an 80 sieve, but which does not pretend to represent with great exactness the fineness of the powdered ore customary in practice. They show that having passed through such a sieve is no proof of sufficient powdering, not that all ores powdered and so sifted are unfit for assaying. This last would be an absurd and illogical conclusion. If an ore be powdered to a fairly fine sand, and then be passed through a series of sieves, say a 40, 60, and 80, in such a state that little or none remains on the first, but the others retain a large proportion, then of that which comes through the 80 sieve, perhaps 2/3 by weight may be even coarser than the powder I have used in the example. Of the rest, most may be of about half this diameter. The weight of the really fine powder may be quite inconsiderable. On the other hand, if the grinding be continued until, on sifting, little or nothing that is powderable remains on the sieves, then in the sifted product the proportions will be very different. This last, of course, is the only right way of powdering. Also, it is evident that so much depends on the manner of powdering that nothing precise can be stated as to the average coarseness of the powder. Suppose, however, by good powdering, a product is obtained which may be represented by a uniform powder with particles 1/20th of a millimetre in diameter, say roughly 1/500th of an inch. Compared with the previous powder, the diameter has been divided by 2.5. Their number, therefore, in any given weight has been increased by the cube of 2.5, which is 15.6. But the value of a sample varies as the square root of the number of particles. Hence the reduction in size and consequent increase in number has made the sample nearly 4 times better than before, and it will be seen that this brings the sampling error within tolerable limits. There are 1 or 2 words of warning which should be given. In the first place, using a 90 sieve instead of an 80 must not be too much relied on. The powder I took in the example would pass through it. It is a question of good powdering rather than of fine sifting. In the second place, a set of, say, half a dozen assays concordant within 1 ounce, where the theory gives 4 ounces as the limit of error, does not upset the theory. The theory itself states this as likely. It is the error you may get in 1 or 2 assays out of 100, not the error you are likely to get in any one assay, which is considered under the heading limit of error. Accepting the result just arrived at, that a portion of 1 gram may be safely taken for an assay if the particles are 1/20th of a millimetre in diameter, the further question remains as to what weight of the original sample must be reduced to this degree of fineness. This may be answered on the principle that the same degree of excellence should be aimed at in each of a series of samplings. This principle is illustrated in the table on page 2. Reader's note described in section 1 of this volume. End reader's note. A fine sand, such as would pass a 40 sieve, but be retained on a 60 sieve, would be fairly represented by particles 1/4 millimeter in diameter. This being 5 times coarser, to contain the same number of particles must be 125 times as heavy. Note the cube of 5. End note. Therefore 125 grams of it can be taken with the same degree of safety as 1 gram of the finer powder. Of such a sand, about this weight should be taken and reduced to the finer powder. If the ore were in coarse sand, say in particles 1 millimeter in diameter, this would be 4 times as coarse as that last considered, and we should have to take 64 times as much of it. 64 times 125 grams is 8 kilos, or say roughly from 15 to 20 pounds. This should be crushed to the finer size and mixed. Then from 100 to 150 grams should be taken and ground to the finest powder. There is, however, a reason why on the coarser stuff a smaller proportion may safely be used. This becomes more evident if we consider a still coarser sample. A heap of ore in stones about 2 inches across would be 50 times coarser than the sand, and an equivalent sample would need to be 125 times heavier. This would amount to about 1,000 tons. Experienced samplers would say that under such conditions so large a sample was hardly necessary. This is because I have assumed in the calculations that the grains of copper pyrites, for example, were all copper pyrites, and the particles of gangue were free from copper. This would be true, or nearly so, for the very fine powder, but far from true in the case of the ore heap. In the heap, probably few of the stones would be pure ore, and still fewer would be free from copper. The stones would differ among themselves in their copper contents only within certain comparatively narrow limits, and it is evident that if replacing one stone by another, instead of resulting in the gain or loss of all the copper one or other contained, merely affected the results to 1/10 of this amount, then a sample of 1/100th of the weight, say 10 tons, would be equally safe. It should be remembered, however, that while the man who samples on a large scale can safely and properly reduce the size of his samples on this account, yet the principle is one which counts less and less as the stuff becomes more finely divided, and ought to be ignored in the working down of the smaller samples which come to the assayer. The end of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer.